Hey everyone, welcome back. This is Sailing the Sea from Buckeye CTF 2024. It was a while ago, but I'm a little bit behind on my videos. I really like this challenge. It's not a traditional CTF challenge. It's more of an educational style challenge, but I think it just covers a really good fundamental topic that we'll talk about, specifically proc self maps, or just the mapping of segments within a process address space. We're going to talk about ASLR. I learned something new about stack-based ASLR. Turns out there's two different randomnesses introduced into the stack, both the page and where the initial stack frame is, which we'll talk about. And we're also going to talk about a useful tool for finding pointers from one segment that point to another segment that is useful in lots of CTF challenges. Like I said, it was a great challenge. It was written by Corgo. Let's get started. This challenge has a zip file, and in the zip file, there's a challenge.c, a Docker file, and some of the libraries. The challenge is very simple. So looking at the C code was given, thank you. Looking at the C code, there's two parts of it. There's the sail function and this report function. And the sail function is just arbitrary read. So they're giving us the arbitrary read gadget. You enter a address and they tell you the uint 64 at that address, and we can query as many times as we want. Once we've done all of our querying, what it's going to do is it's going to open up proc self maps, and it is going to ask us the location of all the different segments within the process space. So step one, what is proc self maps? Well, let me clear this. So procfs is a virtual file system that allows you to query different process information using your file system. So you can do proc self maps, and what this is the procfs, like I said, that virtual file system. Normally you would put the process ID. Let me go back. So I can tab. Yes, these are all the different processes that are running. Instead, you can use self to reference the current running process. And so in this case, self would actually be the cat process, because we're going to execute cat. This is going to be an argument, and so we're within the context or execution context of cat. And then we're going to ask for maps, which are the memory maps. It's going to print out a bunch of stuff. So you can look at it like this. It's kind of messy. I'm going to go for color coding, syntax highlighting. And to do that, we can use pwn debug within GDB and look at the same thing, and it's just much cleaner. So I'm going to run GDB. I'm going to turn ASLR on, because normally I have it off if I run GDB manually. Then I'm going to run the program. I'm going to cancel it. And then I'm going to use the command vmmap. So this will show virtual memory map, all of those different segments, but it'll be nice and colorful. Okay, cool. So to reiterate, the goal of the challenge is to find the starting address of each of the individual or each of the unique segments. So this is a segment. This is the segment for the main binary. So we would need this address. We can see that the address is 400,000. This just means pi is not enabled, position independent executable. And so this address is always at the same place. So that's useful. So this is like our starting point. Like I said, as part of the challenge, we get arbitrary reads. So we can give it an address, and it'll tell us the value at that address. So we have to start somewhere, and since pi is off, this is our starting place. So we know roughly the address of all the symbols and things that are loaded in here. So if we can find a pointer in here that points to other things, we can start, uncovering the rest of process space. Because by default, ASLR is on, and we can't see anything. I guess I didn't talk about ASLR, but ASLR, address-based layout randomization, it's just a way to make exploitation more difficult, which is a good thing. And so things are moved around within process space. They're not always at the same address. And so you can't just like hard code where libc system is, which is a common exploit technique. You can't just hard code that into your exploit script and jump there whenever you have like an arbitrary execution primitive. And so now you also have to have an info leak and figure out where that function is and then jump to it. But yeah, just based off of, and also another one is the stack is another good area that's randomized. And so because of it, it used to be if you did a buffer overflow, at some point you're going to overwrite the return address, and that return address is another address on the stack. But now that it's randomized, you don't know where that return address is on the stack, and so it just makes like buffer overflows hard. It just makes all exploits harder. It just means now you also have to find an info leak to figure out where you're trying to do something, and then from there you can finish your exploit. But anyways, ASLR is on, but pi is not on. So the main binary itself, the challenge binary, is not randomized. So it is at this known location and will always be at this location, but everything else is randomized except for vsyscall, which we'll talk about in a second. Cool. So we start here. This was the first segment, and the different segments, we can see this one has read permissions. This one has read execute. So this is where all of our functions are. We have two more read sections. So this could be like global variables and other stuff like that. This is read write. So this is where our global variables are that we can both read and write to. The global offset table is also in here. And here is our heap. This is one of the dynamic memory sections. And this is where you can allocate like a chunk of memory, and you can use it in between functions and stuff like that. So at some point, we need to figure out this address. And somehow, like I said, we have to, by asking the program what is at different addresses, we somehow have to jump eventually to heap and find this address. Here is libc. Libc is super important. It's pretty much included in, or not included, but it's pretty much used by every single binary written in C or C++ and probably every language. This has all the functions for, like if you want to make a syscall, for example, you usually don't make a syscall directly. You'll use a wrapper in libc for like, so if you want to like open a file or read from a file, you're probably going to use a libc function. The malloc implementation is also as part of libc. And libc has stuff for everything. As part of libc, there's a couple more of these anonymous sections. These were most likely mmapped in. So mmap is memory map. It's just a way to kind of create usable address space within a process. And so these were mmapped. They're just anonymous, so they're not named. But you can mmap for if you want a chunk of memory to do stuff with it, or you can also memory map a file. So if you have a file on disk, you can map the contents of a file into the process. And so you can directly edit the file even just by modifying the memory, which is pretty fun. These probably hold the thread local storage structures. So each thread will have certain variables that should be unique to that thread. So stuff like that will be stored. So fs, which is a register, will be pointing in here. We have the loader. So the loader's job is when there's ASLR, this binary doesn't know where any of the libraries are for libc. Because libc is going to be randomized within the process space during each execution. This function just doesn't know, or this code doesn't know where to jump. And so the job of the loader is to wait till the challenge binary needs one of the libc functions, and it'll resolve the correct address, and then it'll actually save it in the global offset table in here. And so future lookups are much faster. But the loader's job is just to figure out how to match addresses to symbols. Next, we have the stack. So, the classic place for buffer overflows and stuff. The stack holds a bunch of stuff. We won't be talking about it, but there's like auxiliary vectors, which is information that the kernel passes to the program, environment variables, the arguments, and then all of the function frames are also on the stack. So every time you call a function, the stack grows downwards, I guess upwards in this diagram, but from a high address to a low address. And each function gets its own little local variables and the return address and the return RBP and stuff like that. And then we have these three things here. These are fun. I have another video on the channel called Security Topics VDSO or something like that, where I go in depth on this. But I'm going to start with this one. So when you make a syscall is a little bit slow. And there are certain things that are syscalls, like getting the current time. Like a process doesn't know what the current time is. It has to ask the operating system what the current time is. And you can imagine if you have like a logging application, like the log should have the timestamp in it. Anyways, if you ask the operating system for the current time, when you make a syscall to do that, it has to go from user space or user execution to kernel execution, and that can be kind of slow. And if you're just asking for the time is, like, why are you going into a privileged execution mode? So the smart people that be created vsyscall at first, and this is a way to kind of speed up, and so you have a kind of a user cached get time of day implementation that is much faster and doesn't require user space. I'm not sure exactly how this used to work. If it works similar to VDSO, what's actually happening is this is another memory mapped region, and it's done by the kernel into user space, and it just contains some kernel variables, specifically the get time of day variable and some like clock cycle stuff. And so when you call one of these functions, it'll actually just read from this memory mapping. A little bit under the hoods, but so vsyscall was created first, but it doesn't have ASLR or doesn't respect ASLR, so it is always at the same address. But since it's at a constant address, we can look for ROP gadgets and other juicy targets as part of this, which is not good. Everything should respect ASLR. But Linux is also very strongly opinionated, or maybe not opinionated, but strongly enforces backwards compatibility, which is a good thing. And there are probably programs that directly call functions within vsyscall, and they would break if vsyscall just randomly started using ASLR. So to get around this, they created VDSO, which is, again, similar to vsyscall, but now it has ASLR. This is great. So now we have a ASLR compliant implementation of these like get time of day functions and other functions that are kernel functions, but shouldn't really require like a full context execution swap or whatever. Cool. vsyscall now. So if we still left it in, you could still use it for ASLR. The attacker doesn't care if VDSO exists, you would just use this. But I believe now, if you jump to an address in here, it triggers a trap exception, and then the kernel actually does the existing syscall implementation of get time of day. So it is now the slow implementation to use this, but at least it is backwards compatible. And so yeah, that is all the segments. So that is what is in your process when you're running one. There could be other libraries in here. So this process only has libc, but you could have like libm and libcrypto, and you can make your own libraries. They would be somewhere over here. And you can do anything you want. Like you could map more regions. It just happens that this is what the process is, and this is what, if you're doing CTF challenges, this is pretty much what every single process looks like. So this is everything in your process space. Cool. So getting back to the challenge, like I said, we need to figure out this address, this address, this address, this address, and these other 3 addresses. And we're allowed to, like I said, we're allowed to query an address for its value. So the first thing is, like I said, we have addresses here. Probably the most useful thing to do would be to get to libc. Unfortunately, there's no pointers from here to the heap. And how you find a pointer from one segment to another segment is using a tool called P2P. This, for some reason, does not exist, or maybe I can't find it on the pwn-debug docs page. This command isn't documented, but it is a valid command. You can search for it on the GitHub repo, and it is such a useful command. So I can say pointer to pointer. I'm going to ask pwn-debug to find me a pointer in chal that points to libc. And kablamo, we have a whole bunch of pointers. So we can see these are pointers within the chal binary. So you can see it's in this address space, and they point to something within libc. And so we can start calculating offsets and having fun with this. So at this address, this is a constant address, it'll always be the same. This address points to libc start main, which is a symbol within the libc binary. So cool, we already have our first leak. So if we send this to the challenge binary, it'll return us this value. With this value, we can now calculate the base of libc. So libc, it's going to be somewhere in here. Libc, like I said, it is always, because of ASLR, it's always going to be randomized in memory, but the symbols within libc are always going to be a known offset from the base of libc. So it'll start at this address, but this symbol will be a known offset from the base of this address. So we can take this symbol, libc start main, and we can subtract the offset of libc start main from the start of libc, and we will have the base of libc. So we just found our first segment address. Cool. And that is pretty much what we're going to be doing for all the different segments. So we're going to use this P2P command, figure it out, and put it into our solve script. I'm going to jump over to the solve script, and we're just going to cover a little bit more, and then we're going to go back and forth between all the different segments and just kind of show how they all line up. So this is the solve script. This is my standard pwn-tools stuff that I just have in all of them. Nothing too exciting, just ignore some warnings, load, set the context. I use tmux for debugging. These are some generic helper functions, load the binary, start the process, and this is where the challenge actually starts. So this is the query function, so you can give it a address, and it'll return the value at that address. And like I said, this is just the part of the challenge. It says captain, you give it a value, it says gathered, and it gives you the integer. I assign elf address, so the base of the main challenge binary is at 400,000 in hex, and I just print it out. So that first query that we just showed, so like I said, it was at address 403ff0. I'm going to switch back. It is this one. At address 403ff0 is the symbol, the libc symbol for libc start main. So I query 403ff0, I get that value, so libc start symbol, and I subtract the value, the offset from there to the base of libc. So since libc, we haven't assigned a base address yet, it assumes the base address is 0. So the symbols, this value is the address of the symbol within starting from 0. So if we just take this value and we subtract where that symbol is in reference to 0, we will have the base of libc. And so now we have our first leak, which is a libc leak. Yeah, which is pretty neat. The fact that you can do this is just so useful. So libc, we just loaded it from using pwn-tools elf. It loads it in, it calculates the symbols and all their offsets and all that stuff. And now we can just ask it where a specific variable is using this. And yeah, pwn-tools just does it for us. And then we can set the base of libc. And from now on, if I was to do or print this out, libc symbols, this, it now is updated with the base using libc.address, and it'll have the correct address for my process with the ASLR and everything, because now we know what the base address is. The next segment we're going to look for is the heap. So the heap is located here. We could try to see if there's a pointer from the main elf to the heap, and sometimes there is, so it would be from a global variable. We can do chal heap, but in this particular challenge, there is no heap address within the challenge segments. But we have a libc leak now, so we can ask from libc, are there any leaks to the heap? And there definitely are. It takes a second because it's scanning all of memory to find an address, and we have two of them. So we have this variable called mp plus 96, don't know what that is, and it is pointing to this address, which is in the heap segment somewhere, and we have main arena plus 96. It is also pointing somewhere within the heap. So sweet, we can take this one. Let's see where it's pointed to. So this is A7D, and if we look at, that is A7D. So this one is actually pointing to the start of the heap. So this is the exact address we need. We just need to figure out where mp underscore 96 is. And thankfully, using PwnTools, this is very simple. We are going to, again, use the query function from the challenge. We are going to query the libc symbol mp, which is, we just say libc to symbols mp. We add 96 like that, and now we have the heap base. So 2 down, a couple more to go. The next one is the stack. This one is fun. I was supposed to record this video yesterday, but I went down a rabbit hole that took me like 4 hours. So instead, I'm recording today, but I'll talk about all the fun stuff I found a little bit later, though. So this is the stack. The stack is at the top of the process space. So we need to find a leak here from somewhere. I use libc. Libc just has addresses to everywhere, so I do p2p libc stack. So find me a pointer from libc that points into the stack. For a different challenge, I know that it has the process name in there, or the program invocation short name, which is a useful leak target. One thing you have to be careful about when leaking stack addresses is every time you call a function within the program, you're going to push down a stack, or put a new stack frame onto the stack. And so if you call a bunch of functions, like your stack relative offset could be different. So you really want a stack leak that is like very high or very low in the call chain, so that there hasn't been too much mucking around yet. Program invocation short name is passed in, so this should occur before the stack frames, so we should be immune from all of that, which makes things much easier. We can also use libc argv, which will also occur higher in the stack, but less clobbering because it goes the other way. So we could take any of these. I'm not sure which ones I took. I took program invocation short name. So I said, please query me the address of libc symbols program invocation name, and then I AND it with some bitmask, and then I added OX1000. So this is where my research started. I'm going to just talk about a little bit about this, and then I'll go into depth after the challenge for those that are interested. But the stack is pretty finicky. Even though this is not going to be mangled by stack frames, calculating the top of the stack just has a lot of padding, null bytes in there for some reason. I've seen this on a bunch of different challenges, and I never really sat down to research it. I'm not sure why. I asked around. No one seemed to know why. So that's why, again, I had to do some digging, which was fun. But basically what you can do, instead of subtracting it from a known value or anything like that, you can just apply a bit mask. So I'm just doing FFFFF000 and an AND. So it'll just, if we go to this, it'll strip off everything except for these. It'll keep everything except for these last three. And we just hope that it's here. So in this case, I had to add in an extra O1000. So the value leaked must have been like 7FFD, F54, FE, something. Like I said, when you AND it, you only keep these bytes, and then I add 1,000 to make it a D instead of an E. And you just get that from guessing and playing with it, nothing special. That gets us the top of the stack, but the stack goes this way, and so we need the bottom of the stack. And we can see the stack is 21,000 bytes in hex, and so we just subtract that value. So from the stack to the bottom, minus 21,000, and we're there. And cool, now we have the stack base. We need the loader. Again, this is the thing that does symbol resolution due to ASLR. And to do that, looks like I did libc, so we can do pointer to pointer, libc, ld. I'm not sure why I used libc. There are good pointers within the main challenge binary. I just didn't use them for some reason. And we have plenty of targets to pick from. So again, we can pick any of these. This is an address in libc, and it points to the loader. The specific one I chose, I guess, ends in an FAO. So we're looking for an FAO. I picked this one. So something that points to RTLD global. So FAO, this. And so because there were no symbols here for the libc ones, I guess I could have used this one. I don't know why I picked this one. I guess I was just rushing through the CTF. I just calculate the offset manually. So this was the address, the specific address, this address. I calculate the difference between that and the base of libc. So this is just a known value, a constant value. So this is the constant offset from here to the base of libc. If we had the symbol name, we could have done the same libc symbols trick. This particular memory address doesn't have a symbol. So we just do that and we add it to the base of libc so we can recreate it. Nothing too special. And we take that value. This is going to return this value, 6040. Yep. A value that ends in 0400, 040. And from here, we just take this and we calculate to the base of the loader. One way you can do that is VM map and then the address, and it'll kind of tell you, although not really, it'll tell you what segment it is, but really we want to the base of the initial or the very first segment, which is this one. And so you can just subtract the value you get from this value and you'll get how far it is within the loader. So we're just calculating to the base. Yeah, that gives us the loader base. And then we have the VDSO and VVVAR. These are at known offsets from LD base. Actually, just kidding, I lied. They're offset from each other, but not a known offset. VDSO base, we can find an address to it in the loader base. So we do pointer to pointer from the loader to VDSO. And we found it. We're going to talk about this a little bit later. This is the link map structure within the loader, most likely. I guess some of them, probably not all of them though. So we have this structure or this address, and it is pointing to this VDSO address. So we're going to, again, do the same sort of address copying manipulation. So I guess, oh, actually, there looks like there's a direct reference to a base somewhere here. So DC8. Is there a DC8? DC8. So RTLD global RO plus 744 goes to this address, and this address is the base of the VDSO. So by querying this one, we will just directly get the base, which is less math for us. So that's what I do. I do LD base plus this. I guess we could have loaded the symbols. So we could have loaded LD in and then done, the whole symbols. I guess I just didn't do it again. This is CTF, so I was probably rushing through it. We'd also have to load the loader, which I think we have. Yeah. So we could have done LD to 35.so if we were doing things correctly, and then whatever this was, LD symbols, and then this symbol plus 744. But again, this is CTF stuff. But yeah, from there you get the base of the VDSO. Then from the VDSO, it is a known offset to VVAR, and you calculate both of those. I don't have vsyscall up here, but I just sent it here. Again, it is just a constant address because it doesn't respect ASLR. So you take all those values you calculated and you send it to the process and you're done. Again, it's not a real CTF challenges, but it just, makes sure you understand the fundamentals, which I love. And like I said, I learned something very new, which I guess we'll cover now. So why is it that if you have a reliable leak within the stack and it is near the top of the stack, so it's not being clobbered by function frames, why is it that you can't reliably calculate the offset to the top of the stack? Or why is it different on every invocation of the program? Like ASLR will randomize the starting location of the stack, but if you have a relative offset, it should be constant. And if you play with if you open it up in Pwn-debug and you look at like what's in between that difference, it's just a bunch of null bytes, but it is a different value every single time. So like, what is inserting all these null bytes into the stack? So I asked around to see if anyone knew. I did a bunch of Googling. It's kind of hard to Google for, but I just couldn't find anything. So eventually I started looking in the Linux kernel source code, and I think I found it. I also talked about it on Twitter. I have a whole me just debugging the issue. And I also talked about it on Discord, and I got some help from a couple people in Buckeye. And eventually Corgo also independently found this. So I think we both agree that this looks like it, but I've never heard anyone talk about it, and it's pretty fun. So the punchline is that I believe that there are two different forms of randomization that occur to the stack. So this is the Linux source code. This URL is elixir.bootlin.com. Super useful tool. They have the source code for both the Linux kernel and glibc and a bunch of other open source projects. But super good. You can click on symbols and you'll find other references to it. Just good for trying to grok code. If you do more heap exploitation, this will probably be open quite a bit. But anyways, this is the call that does the kind of standard randomization of the stack. So randomize stack top. We can click on it, and here is where the ASLR takes place. So it's going to calculate a random variable. It's going to apply the stack mask, so how many random bits we're going to apply to the stack, and then it's going to just shift it over for the page size. Cool. If we wanted, we could see how much randomness is actually used. I don't know, maybe this one. And we can see the stack random mask is So I guess if it's 32 bits, this is how much entropy we get, and if it is 64 bits, this is the mass that's used, which is basically how much entropy we get, which yeah, pretty cool. So anyways, that is the ASLR that I think everyone thinks of when they think of ASLR for the stack. But again, it turns out there's like that big chunk of null bytes, and eventually I found this, and so this is arc align stack that is also called as part of bin format. Oh, I guess it doesn't matter too much, but the file we're in is called, well, not this one, is bin format. This code, it's in the kernel, and this code is called when the kernel is starting a elf executable or an elf process. As part of that, eventually it's going to call arc-align stack, and so what you do is you pass in a stack pointer, and it is going to subtract some random value between 0 and 8192. And so this is the actual starting frame, or roughly the starting frame. So for some reason, it is also picking another value between 0 and 8000, and randomizing the stack pointer within the already randomized stack page. So that's very interesting. I think me and I think Corgo also mentioned that I think what we think is happening is it seems like there was an initial version of ASLR, and it is this one where it's just randomly, the stack pointer is just kind of randomly aligned in the predefined stack location. And so kind of an easy way to get, at least some ASLR within the stack. And then eventually the real ASLR with, the many bits of randomization was added a little bit later. But this was the initial version, and it was just never removed. That's my understanding. There's a good article here that talks about it. So it looks like Arjan van de Ven wrote the initial ASLR patches, so thank you for that. And it talks more in detail about what they are and why they're important. But pretty cool. So it turns out the stack has two different forms of ASLR. I had no idea. So next, I looked around to see if anyone else had clever solutions to the challenge. Someone else posted a solution. It looked just like my solution, very similar. But Solar Debris had a very interesting comment. It says that they looked at the DL link map for LD using the link map command in Pwn tools, and this will get the VDSO and VVAR, and it is like OX 4000 bytes away. So interesting, the link map structure. So I had to do a little bit of research about this. It sounded familiar, but I just never use it. It turns out, so we can do link map. I do wonder if they meant Pwn debug and not Pwn tools. Could be wrong though, but we're going to use the link map tool within Pwn debug to play with it. So if we do a link map within the process, we get this information. And so what is this? We can look at the actual source for it. It is this. So this exists within the loader, and as just a quick refresher, VM map. So this is the loader. The loader's job is symbol resolution. So when the challenge binary needs a symbol, but within libc or VDSO or something like that, but ASLR is on, it doesn't know where they exist. So through some trampoline code, it eventually calls into the loader. The loader will figure out where that symbol address is within libc, and eventually it overwrites this entry into the global offset table. And so all further executions of that are much faster. For example, there's a variable called puts. And so at some point, this challenge most likely calls puts. We can actually ask, so we can do GOT, global offset table. It did call puts, so it needed puts at glibc. Eventually, at some point, the very first time this was called, it called the loader because it doesn't know where puts exist within libc, and the loader figured it out, and it put the value into the global offset table at this known address, and this is the address of puts. So for the loader to work, though, it needs to know the base of all of these different segments. So this is a pretty prime target for doing this challenge. If the loader already knows the base of everything, I think it's a little bit overkill because we can just use the p2p command. We don't actually have to parse and think about all these structures because there's pointers everywhere. But I bet if this challenge had more memory mappings or like more objects, or sorry, more libraries like libm and libcrypto and all that stuff, it would be fun to just kind of like parse them all out of the link map structure. But anyways, we can do link map again. So there are 4 mappings, these link map structures, and also this is what the link map structure looks like. It is struct link map. It is a address, and then the name, and then the dynamic section of the shared object. I'm not too sure what this is, but I guess it's just a pointer to whatever some dynamic section is. And then it is a linked list with the next and previous. So the 2 things that we care about are the address and the name. So pretty cool. So we have the address and the name. So it is saying, the name and the address. So we have the main challenge binary. It says address 0. I think it's just because it's the main challenge binary and pi is off, so it doesn't really do anything. Then we have, and you're going to be asking for symbols from this, so a little bit strange that it would be needed for the loader. Then we have VDSO. So it has the string VDSO, and it says that video starts at 554000. You can see 5554. Then we have libc, which is at 548, and we go to libc, we got 548, and we got the loader itself, which is A9C and A9C. So cool. The structure just contains the base address of all the different segments, which is what we needed. And yeah, what a pretty clever way to think about this challenge. If you want to print out the actual objects too, you can do that. So if we want to, example, print this out, if you print out the address, that's not quite right. You can dereference it, but it doesn't know the type. But if we dereference it with the type, so it was a link map pointer, you can actually see what the structure is, and it'll fill out all the values for you. So this is the address. This is the name, so just the pointer to the string, so Linux VDSO SO1, and then this is that dynamic segment, I guess, and then these are the forward and back pointers because it's a linked list. I'm not really sure why all this stuff is included. But yeah, anyways, super fun educational challenge. It was fun to go into the Linux kernel source code and learn something new. And so thank you to Buckeye for hosting, and thank you to Corgo for writing the challenge. And I'll see you at the next one. Cheers.